Fair enough. Let me know when you're ready to do.
I'm ready.
Biophysics is pretty cool in that you get like a huge range from either classically trained physicists who then want to apply things to biology, or biologists who want to learn more quantitative tools to apply to their biological research.
If you start from sort of a baseline of the real physical, mathematical, foundation, then you can kind of do anything. That was sort of my idea.
Okay, so my name is Meg Taylor. My undergraduate degree was in chemistry, biology, and statistics.
I've had quite a weird way of getting here, I suppose.
I didn't know what the PhD was about, had no idea what the requirements were, what it entailed.
After having done a career with the military and being an unmanned aircraft pilot, I decided I kind of wanted something that was a little bit more intellectually heavy.
Especially getting into grad school and starting research, it's so much about the creative process and coming up with ideas and refining those ideas and trying to stick with them. And that's exactly the same as songwriting, at least, composition.
Engineering curriculum in India mostly is kind of an umbrella curriculum that teaches you everything. So that's how my mind kept on drawing the links, and physics has been always very stimulating, intellectually stimulating to me. So I always wanted to apply physics to biology.
So I had some background in math, I had heavy background in physics because of engineering, and the biology all kind of met in one place and biophysics made sense.
I'm studying association of transmembrane helices when they are in the dimer state. In my case, I am interested in understanding the energetics behind that process and how changing sequence at the interface of the dimer will affect the stability, the thermodynamic stability.
To know how life could evolve, it is important for us to look how life has evolved and come to the current form that we look at right now. So I'm working on a Rubisco protein complex. And so what I look at is the ancestral form of the protein and the modern form of the protein and try to understand how it would have evolved through time.
I wanted to have something more applicable than answering a foundational research question. So what I currently do is kind of in the realms of protein engineering and synthetic biology. So rather than discovering a why of science, we're taking the why that we already know and we're applying it through machine learning and protein engineering to make better outputs for medicine, biofuels, food chemistry, things like that.
The main protein kind of at the center of our research, or protein complex, is the kinetochore. And because they're diffraction limited, recently we developed a expansion microscopy protocol. This method was created from a group in MIT, and he originally just said, what would happen if we take essentially baby diaper polymers, put them inside of biological samples, add water, and blow them up? And it turns out it works. But his original method expanded 4 times, and we were able to optimize it to a degree where we expand the cells 12 times.
When I got here, it was like a feeding frenzy for me. I was like, oh my gosh, there are all these resources. I just want to sort of do everything.
There are a few labs in biochemistry that are associated with NMR-FAM, Nuclear Magnetic Resonance Facility at Madison. It's a fantastic facility. There's staff scientists that are able to help train graduate students and outside researchers that come with their samples. You have an idea for a project, you can make your sample. You can ask one of the staff scientists to help you pack it into a rotor, which is necessary to run the experiment in the spectrometer. You can then work with a staff scientist to evaluate your sample, plan the proper experiments, and then get training to run those experiments with the staff scientists and then have help analyzing it.
So U6 is a complex composed of U6 siRNA and several proteins, but people know little about how those RNA and protein come together. And so using this Cosmos, I can observe different protein factors comment the single RNA molecules. So the cool perspective of this is it's a single molecule technique. So you can actually define different subgroups inside one kind of molecules.
Cryo-EM as a tool in general is exploding, and right now is probably the best time to get into cryo-EM, because ever since the resolution revolution, if you will, of 2016, the amount of structures that are being deposited into the actual PDB are almost primarily coming from cryo-EM right now. It doesn't matter what type it is. If it's membrane-bound protein, we can still get it. If it's a difficult protein that will not crystallize, it's possible we can get it. If you're not exactly a power user and you're still in a biochemistry lab and still interested in doing cryo-EM, the facilities will assist you with your samples.
It's just, this is the science, this is the question, can I answer it? And there is so many resources that I can usually go and be like, oh, I would like to learn this to try to answer this question.
Yeah, well, and a lot of these tools are getting paired up. So, now they have single cell sequencing with image processing. You could do like tissue image processing, spatial transcriptomics in a tissue and stuff like that. So there's more of a systems capacity as these tools get paired together, and that's super exciting.
Madison's program was the one program I could really customize my lab for me. Like, you can go super heavy physics here, or you can go super heavy biology, and there's everything in between. You can find a lab that's like purely wet lab, or it's purely computational, and everything in between. But our rotations, they're pretty quick, and you do 3 of them, and they're 1 month each.
And it actually gives you a better opportunity to start with your PhD thesis faster.
I felt it was the perfect length because you got to get to know the professor, talk to them a few times about the science they're doing, shadow some graduate students.
You are not restricted to work with a specific list of faculties that are part of the program.
You have to choose one mentorship style that works with you, and there's definitely a range of it that works.
There are certain people for whom the lab environment is going to really matter. And there are certain people for whom the content is going to really matter.
I was more concerned about the people and the PI. Like, do we get along? Is it going to be a good fit for 5 years?
When I chose my PI, that was one of the conversations I had was, are you supportive of people in industry?
There's a lot of support for doing like science policy and science communications and science education. And
our requirements for classes are very flexible. So if you want to add in like a PhD minor, like in something like life science communication, for example, you have the time and opportunity to do that.
I've learned a lot of like writing skills, a lot of people skills.
I'm here because I love science and it's what I want to do. And I really like mentoring and teaching.
It seems to be more the consensus now that not everyone will become a PI, and there are a lot of ways to succeed.
But I haven't ruled out academics yet, because I really do love teaching. I did it for a long time in the military, and I think that sense of giving back and getting people excited about science is always, when you see someone light up with that, I get it, that totally makes sense with something that's kind of complicated. It's really rewarding.
So in content and in practice, in this specific program, students have a lot of flexibility. We're all over campus in several different departments, and you can kind of just dive into whatever research topic you want and have the sort of support content-wise and institutionally, administratively, to make it happen. Oh, Madison is a great town.
It's a city, but it still has like that small town feel. So we get to have that community with people, but also have some of those big city things like music festivals.
And there are a lot of opportunities for live music that I partake in and play in.
I really enjoy like all the different restaurants here in Madison and different local food.
Also, if you are a foodie like me, you would love the ice cream here.
April through November, there's a farmer's market on the square, Dane County Farmer's Market. I think it's the biggest in Wisconsin, if not the Midwest.
You have quite a diversity of seasons, so you get to really experience changing seasons.
I have learned to really appreciate the summer because the winter is so cold.
You live on the water in the summer, which is awesome.
There are tons of water sports and ice sports.
I kayak, paddleboard, canoe, fish.
The best town I've ever lived in for bicycling.
Pretty much any time but winter. Even then, there's people that brave it and have giant tires and go out there and do it anyway. But
People go out on unicycles on the ice. It's bananas.
You can find nice places to hike.
It's very dog friendly.
We have, I think, 11 dog parks just in Madison.
Madison's not very fast-paced.
Rent isn't very expensive.
People are super friendly here.
Yeah, of course, I got homesick at times.
But it has been quite a nice journey. I've just come here last year, but feels like home.
the biophysics program has been instrumental to my success and growth as a scientist. I encourage you to apply.